Hello there everyone, my name is Crazy Caleb, and today we're going to be taking a look at not symbolic coordinates. Boy, did I think I was done with the not series, but no, we are definitely not done as that suggests. But today we're taking a look, as of right now, the last Speaking Evil module that has a not module. Of course, he's probably going to be releasing more at some time, but today we're taking a look at this one. So this module actually recently just got fixed a couple weeks ago. It had a bug that we could not figure out, and then Exodus comes along and just becomes a god, and then just fixes it. Still hasn't done most of his modules, but I digress. Um, so what exactly are the key differences with not symbolic coordinates and symbolic coordinates? Well, there is a couple big differences here. So let me actually pop up the original manual, but if we take a look, there's going to be a lot of potential differences of which we can get. But the easiest way to tell is going to be taking a look at the actual two displays that we get here. That every time it will always start with an A0 on the actual display, which in this case it starts with an echo 0. Now, how exactly does this help me? Because there could be the potential of there being an A0. Now, if we go through each of the displays, as we can see, we only have 5 options per display. That's going to be essentially the way that we're going to, that's going to be the key here to determine that's going to be which one's not symbolic and symbolic coordinates, because on the left side, it would normally be the entire alphabet in the asterisk, and on the right side, it would be the 0 through 9 in the asterisk. That would be the way that that works. Now, couple of the differences, but that is essentially going to be your key one that you're going to look at. That's going to be the key distinction of which you can take a look at. Um, the second distinction is going to be the LEDs in the middle. There is the possibility of there being duplicate LEDs, or all three being the exact same, um, or all of them being false, all of them being different colors, but they will be all 4 colors present. So there's going to be green, yellow, aqua, purple. There's no new colors. However, there is the possibility of there being duplicates. That is the key distinction here, instead of there being exactly one of each. That's basically the key distinction. Next up, another big one is the actual display up at the top. The display up at the top normally would have only 5 symbols that consists of coffee stain, vortex, and a tunnel, and Pluto, and what's the last one? I believe it is the flag. Yes, it would only consist of those 5 symbols. However, if we take a look at the manual, there is a lot more than those 5 symbols, as we can see. This is basically the inclusion of all of the reverse Morse and cube symbols, essentially, along with 4 additional new ones in this case, these 4 right here. Now, I like to call this bottom one the tsunami in a way. I like to just think of it like that, or like the ball, for example. This one is sort of like, it reminds me of like a Boolean keypad, sort of. Um, it's a bunch of wedges spinning clockwise, like you can call them like the fries or something like that. Um, this one is a square within a circle, and that's highlighted, and like a brown is another square of its own. Um, and then this one, I don't really know how to call this one, but it's got 4 parts sticking out on each side, and it sort of has a bunch of swirly stuff in the center. That's going to be your key distinction. This stuff is not from any royal flush module, which is what the module comes from, normal symbolic coordinates. And finally, your last key distinction is going to be the LEDs on the right side. Normally, these would be stage indicators for symbolic coordinates. However, in this case, all 3 of these guys are lit up. Normally, they'd all be black. That's just the way that the way that we be. However, there's also the possibility of them all being black, which is why I would say the most reliable option is going to be taking a look at these 2 displays here, because of the fact that there's guaranteed to be 5 of them in each individual set. So what exactly are we doing with this module? And if you've made it this far, I would like to straight up say that, number 1, if you don't know how logic works all that well, turn back now. I'm just going to straight up say it now because this module is a logical hellhole. So if you don't know how to do much logic or do logic in your head, just turn back now. Get used to logic. I will leave a link to the actual logic tutorial, the first one that was made, in the description. However, this module is solely reliant on the concept of logic, and everything has to do with this. So keep that in mind. This is all going to be based off of logic. If you don't know how logic works, leave now and come back later with a little bit better knowledge, because I'm going to go through this a little bit fast, and I really don't want to spend time on the explaining the concept of logic throughout this tutorial. So let's get right into this. So what we need to do is we need to take a look at each of these symbols here, and we also need to take a look at the LEDs at the bottom. And what exactly is our goal with this module? Our goal is to essentially try and create a series of of statements that work. And with this, the display is our inputs, and the LEDs are our outputs. And what our two characters are going to do here, what our two sets are going to do, is they're going to be determining the series of logic gates which we will be plugging each of our values in here. So we need to figure out we need to figure out our inputs and our outputs, but our main goal is going to be figuring out what gates, what sets here that we have, we can put into the actual module to return these as what they actually are. That's going to be essentially our goal here, which we're going to use as a process of elimination. So let's get right into this. So what we need to do is we need to take a look at each of these three symbols first. And what we're going to do is each symbol represents the numeric value corresponding to its position in the display, and the truth values correspond to the other two in order. So let's find, for example, this first one being meteor. So let's scroll down, let's find you here. Meteor is currently in the first position, and the numeric values are on the left side, and the truth values are on the right side always. So the meteor is going to be the first position, and the other two positions are going to be the truth values. Note that we're going to be pretty much focusing on the numeric values first, because of the fact that all of the truth values have to do with getting all three numerical values first. So the first thing that we're going to get for this case here is going to be the numeric value of meteor, which is going to be 7 times the number of serial number consonants. So in this case, that's going to be 2 consonants, because we have 2, 2, and a 9, and echo is a vowel. So we're going to be 7 times 2, which is going to be a 14. 14 is going to be our first value here. Let's keep those highlighted, but let's come back to that in a little bit. Next up, our symbol is flag, which is in the second position right here. And the other truth values are going to be 1 and 3, the other position that we're currently not in. So the numeric value for this one is going to be the number of indicator letters that occur after M alphabetically. So the number of indicator letters that occur after M alphabetically. Taking a look here, there's only going to be one of those because we only have one indicator present, and the only indicator that and the only letter that comes after Mike is going to be a Romeo. So that is going to be corresponding to a 1. And then finally, our last symbol is going to be the moon. This one is from reverse Morse. The moon is going to be right here, which is just going to be the 21, which is what our truth numeric value is going to be, and the truth values are going to be positions 1 and 2. So now here's where we get into the actual truth values, because 21. So the truth values of the first one here, meteor, is taking a look here. We need to essentially evaluate whether these are true or not. So if they are true or not, that's essentially what we're going to be doing. Any value is 30 or more, and these values are referring to the numeric values here. In this case, none of them are 30 or more, so this is going to be corresponding to a false. Then next up, the sum of the three values is divisible by at least one of the values. Well, that is going to be true regardless, because because of the fact that we have a 1. Everything is divisible by 1 in itself. That's pretty straightforward. So this is going to be at least divisible by one of the values. That is true. We don't even need to sum it up. However, there might be a rule of which we need to sum up all three values regardless. So let us take a look at the next values here. So we have the flag, which is up here. And here's where the next rule comes into play here. Any sum of the pairs is 10 or less. What exactly do sum of the pairs necessarily mean? This is referring to doing a series of a couple of pairs. For example, let's take a look here. We only have to do 2 values. I don't know why it's like this. There we go. So all we essentially have to do is we have to do a 14 and a 1, for example, and then a 14 and a 21, and then a 1 and a 20, 1 and a 21. That's going to be essentially a sum of pairs. So that's going to be a pair of values. So in this case, 14 plus 1 is going to be 15. 14 plus 21 is 35, and then 1 plus 21 is going to be 22. So now, taking a look at what this rule suggests us, for us, any sum of the pairs is 10 or less. In this case, that is already going to be false because of the fact that we already have 2 of the 3 values are greater than 10, and adding them together will give us 10 or more. More than 10, rather. So that is immediately going to be a false rule. Then next up, both digits of the sum of the 3 values are odd. So let's actually sum up all 3 of these guys together. So 14 plus the 1 plus the 21 is going to give me 36. Now, taking a look at both of these individual digits, are both of these guys odd? 3 is odd, 6 is not. So this is not true, so this is going to be false for this one right here. And then finally, taking a look at our moon down at the bottom here, right here. Taking a look, no digit in the three values occur more than once. That is already a false statement because of the fact that 1 occurs 3 individual times. So that is, without question, false. So, next up, the sum of the digits of the sum of any pairs of values is a multiple of 5. Now, taking a look, the sum of the digits of the sum of any pairs. So now what we have to do is we have to take a look at each individual pair. So 14 plus 1, so 14 plus 1 is a 15. So 15, then we have 14 plus 21, which is a 35. 35, and then 1 plus 21 is 22. So now, what we need to do is we need to take the sum of each of these digits, some of these individual digits, and are they a multiple of 5? So 1 plus 5 is going to be 6, 3 plus 5 is going to be 8, and 2 plus 2 is going to be 4. None of these are a multiple of 5. So because we're taking a look at the sum of the digits of the sum of any pair of values, which in this case was the 15, the 35, and the 22, none of these guys are a multiple of 5. This is also a false. So now we have our inputs essentially figured out right here. This is not what I want to do. So let's save you for a little bit later. Perhaps I need to stretch you out a little bit for some reason. Anyways, I'm going to close this for right now. But essentially, we figured out our truth values for these guys. So now what we need to do is we need to figure out our outputs, essentially. But first things first, we need to take a look at one little rule here. Of the 3 LEDs on the right side of the module, if the top LED is lit, we're going to negate the first truth value of all 3 pairs, and if the middle LED is lit, negate the second truth value of all 3 pairs. In this case, both of these are lit. The top and the middle are white, which means lit. So this essentially means that we're going to be negating our entire set here. So we're going to negate all the first truth values, so false becomes true, false becomes true, and false becomes true. And then we're going to negate all the second truth values, which is going to be true becoming false, false becoming true, and true becoming true. False becoming true, rather. And this is going to be now our final set of inputs and our truth values right there. This is what we're looking at. So now, taking a look at this one here, what we need to do is we need to figure out our positions of each of these aquas, of each of these colors here. So the yellow and the aqua. And now we have a couple of different rules that we need to do. So we need to shift each color one space to the right for each battery on the bomb. And if a TRN indicator is present, we're going to reverse the order of the colors. Note that we must do the shifting one space to the right first before we simply reverse the order of the colors. Keep that in mind. So now we only have 2 batteries, and we do not have a TRN indicator TRN indicator at all. So we're going to simply just be shifting these guys 2 to the right. So we have green, yellow, aqua, purple. We're going to shift 2 to the right, like so. And this is essentially what we're going to be looking at. So now, aqua is going to be the first position. That's going to be a false, false. Aqua is going to be false, false, and yellow is going to be the true, true. In this case, because it's the fourth position over here. So now we have our outputs figured out. Now we get into the bulk of what this actual module wants you to do, and this is going to be how we're going to figure out some of these sets here. So let's actually write down each individual set. So Echo, Foxtrot, Echo, Foxtrot 0, Juliet, and Hotel. There will always be 5 on each side. And then we have 0, 1, 1, 2, nice. Then 7, and then Juliet. And now essentially what our goal is we're going to try and eliminate as many of these gates as we possibly can. As many of these guys in the sets, as many of these characters in the sets that we can. So the pair of truth values indicated by the colors of the LEDs are the desired outputs from the two sets of logical operators whose inputs are the pair of truth values received from the symbols. So what we did here is we received our pair of inputs from the symbols and our pair of outputs from each of the LEDs. That is essentially what we did. And now what we need to do is we need to figure out these 2 sets of logical operators, which when we plug in the inputs, we can simply get the outputs that we need. That is essentially how we're going to be doing this, and there's going to be a little bit of an interesting way how we actually focus on this. So, within each set of operators, operators 1 and 2 of the left set apply respectively to the first and second truth values of each pair from the first and second displayed symbols. Now, let's pause there. What exactly does this mean? Operators 1 and 2. Now, where does this come in? Where does operators 1 and 2? If we scroll down to the bottom, here's where we take a look at the operator sets for each individual character represented here. So operators 1 and 2 is what we're going to be focusing on this time around. And what we need to do is we need to focus on the left set. So we're going to be focusing on these characters right here. So Echo Foxtrot 0 Juliet Hotel. This is what we're going to focus on right now because we're focusing on the left set of characters. These are going to correspond to the first and second truth values of each pair from the first and second displayed symbols. So we're going to be taking a look at true false and true true using the left sets here of operators. And essentially what we're going to do is we're going to try and get the outputting the respective values of the color of the left LED. So this is what we're going to be taking a look at here. So we're going to be trying to get to the false false using the true false and the true true in some way, shape, or form. Now, how exactly does this work? So we're going to be taking a look at the first individual bit for each of these guys here, which in this case is going to be a true true. And then we're going to be taking a look at the second bit, which is a false true, and we're going to try and get this true true to equal to a false, and we're going to try and get this false true to equal to a false. This is going to be focusing on the left set for the left output. So let's take a look at each of our individual characters down here, and let's see if we can cross off any options that simply will give me a true and a true in potentially either the first or second position. So let's take a look. And we're going to use the first bit for each of these individual guys here, so that's going to be a true true in this case. That's going to be corresponding to the first bit of the left LED. And we're going to be using the second bit, being the false true here. And we're going to try to get the false and the second position right here. That's what we're going to be doing. So let's take a look at each of these individual characters. So we have Echo, we have a Foxtrot, a Juliet Hotel, and a 0. Now, let's try and get rid of anything that will give me a true statement for either operators 1 or 2. So let's highlight the operators here. Let's get rid of you. Now, one last thing before I mention this, before we get into this, the operators A and B, which you'll see here, here, and here, what they represent is they represent the truth values of the respective first and second inputs. So in this case, for example, if we take a look at the false true down here, the false represents A and the true represents B. This is essentially going to be the position, and of course, the N in front of it simply means the not, which means we're going to be inversing this. So for example, NA in this first one would be a true. That would be resulting out of true, and we simply ignore the other input entirely. That's what we're going to be doing. That's the way that works, so that's what we're going to be doing. So let's take a look. So now that we got that out of the way, let's take a look and see if we can cross off any options. And normally what I tend to do is to give you a little bit of a hint of how the logic works. I tend to use the alphabets table here just to help me. The ones are obviously represent true, and the zeros represent false. That's going to be the way this works. So let's take a look. And immediately right off the bat, operator 1 for the 0 here, X NOR. If we happen to have a true true for X NOR, that's going to result in a 1, which we want both of these cases to be false. So this is already going to get rid of 0. We simply cannot use that. So get rid of U entirely. Next up, imply. That's another one that we can immediately get rid of, because if we do imply, 1, 1 will give me a 1. That's not going to work, so we'll get rid of U entirely. Next up, for Foxtrot. Foxtrot, operator 1 is XOR. Okay, that works because of the fact that true and true, we need to have exactly one of them being true in order for them to return true. However, we want this to return false, which in this case, if we plug in 1, 1, that will give us a 0. That is exactly what we want. So Foxtrot is a possibility for this first one right here. And if we take a look at the second operator for the second bit, for the false true, we need both of these guys to be false for it to be true. However, we have at least one true present, which in this case, 0, 1, is going to give me a 0. We need our second bit to be false. Foxtrot is a possibility as of right now. That is really, really good for us. Looking at hotel immediately, though, hotel for the true true is going to be, for the first operator, is going to be representing for the true true is an alpha, which is going to be just true. That's the first bit that we're looking at. So that's already going to be false. So we're going to get rid of hotel. Perfect. Okay, so goodbye hotel. And then Juliet, or we need to have at least one of them true for it to return true. So in this case, this is actually going to be a false because we're not going to be using Juliet at all. Because what we have here is we have a true true. True true returns a true, as you would suspect. So this means that essentially this would return as true, which we need to return false. So this is going to be getting rid of Juliet. And now, this actually confirms for us that Foxtrot is going to be used on the left set because of the fact that we're able to eliminate all of the other options. That is really good for us because of the fact that we only need to consider that option now. So that's perfect. So now let's take a look at step 2. And sometimes you can get really lucky with this, and you can actually just get the only option. You can only be left with an option for the first little bit. There is, of course, some cases where you're going to need to use the third operator rule here, which is probably the most complicated of them all. So now we're going to take a look here, and we're going to take a look at operators 2 and 3, which is going to be these two guys right here. We're going to get rid of the foxtrot. So we're going to be taking a look at operators 2 and 3 of the right set. So we're now going to be using the 0, 1, 2, 7, and Juliet. And essentially, excuse me, we're going to be using the first and second truth values again. That makes sense. First and second truth values of each pair from the second and third displayed values. So this is going to be the second and third displayed values. So this is going to be the true, true, and the true, true. That's perfect. So true, true, and true, true. And what we want it to return to is going to be the operator outputting the color, outputting the respective truth values of the color of the right LED. So we're going to be trying to get the right LED, which is the true, true, which should not be that hard to do. So that's actually perfect. And we're going to try to get that. So this is from the second and third displayed values, outputting to the respective truths of the right LED. So we're going to be taking a look at the right LED as our output right here. And this is all going to be within the right set, as we mentioned here. So this is going to be focusing on you guys. So let's take a look and see what you guys have to offer. So 0, 1, 2, 7, 7 in this case right here, and Juliet. Let's try and get rid of as many options as we can. Now, not imply by. So what we have here is an implication, and we're simply going to negate the result that we get from it. So we have a 1, 1 for the true. It's always going to be a 1, 1, by the way, for the inputs that we have. And remember, we're going to be using essentially the first bits of each of them, so in this case, the true and the true, and we're going to be using the second bits, the true and the true, to evaluate each individual statement. So, so for operator 2, we're going to be using true, true for imply. So we're going to be getting a true from that. However, we're going to be negating this result because it is a not implied by, which is going to return as a false, which we do not want. We want this to be true and a true. So we're going to get rid of 0 because this operator does not work for us. Next up, imply by works. That is perfect because we have a true, true here. However, for the second bit, not alpha, we have for this one right here, so alpha bravo, we're taking a look at the alpha position of the second set right here, which is going to be essentially negating this result, which is going to be a false. That's going to be the statement for this, which is not what we want. We want them both to be true. In this case, the second truth that we have right here does not output to a false, so this 1 is also going to be getting rid of 2. So we don't need you anymore. Okay. Taking a look at NAND, not AND, which is essentially the opposite of AND. AND is only true if both of them are true. NAND does the exact opposite. So we want to do a 1, 1, which will result in a 0. That's not going to work for us. We don't want any falses in this case, so 2 is also going to be getting rid of. Goodbye 2. Next up for 7. Ooh, this one actually works right here. 7 has the potential of working because if we take a look, AND is going to be true if both of them are true. If we pop up to this AND right over here, perfect. That returns as a true for the first bit. That works. And then finally for the second operator, the operator 3 in this case, is an XNOR. So we're going to take a look at the second true, true. And if we take a look at the XNOR, XNOR wants us both to have, these both need to be the exact same values. So in this case, a false, false, or a true, true would return as a true, which in this case, we'll have a true, true. That is perfect. So this second bit will return as a true, and the first bit will return as a true because we have an AND. So this means that this is a potential possibility for this to actually appear. Now, taking a look at our last one, Juliet, because we still have the possibility of there being a Juliet in this case. Operator 2 is an AND. We did the set. We had an AND at operator 2 for the set 7 right here. So that means that that's already true. However, operator 3 is a not AND. So this means that we had the exact same case from beforehand, being a true, true. True, true would give us a false for not AND. This does not make sense. So this means that Juliet is going to be gone. Goodbye, Juliet. And now we're actually left with 2 perfect sets, being a foxtrot and a 7. Both of these sets actually do work. However, I want to make sure I explain the last rule and how this actually works, because of the fact that it's a little bit tricky. So, we actually do have our answer here. It's guaranteed to be Foxtrot 7 because of the sets that we've tried here. And most of the time, you could actually get really lucky and actually eliminate it by step 2 in this case. Or it potentially have a only like 1 or 2 characters left. 2 characters can be potentially left, but in some cases you can simply get both these characters that you need, set it up to Foxtrot 7, and you should be good to go. However, this last little operator has a few additional rules that you need to pay attention to. So operator 3 of the left set. The left set is going to be over here. We're going to be using operator 3 of the left set and operator 1 of the right set. This is where things get a little bit interesting. So we're going to be using operator 3. So we're going to be taking a look at, for example, say we have the last value being a foxtrot. In this case, foxtrot corresponds to operator 3, which is not imply. And then the bravo, or excuse me, that's the alpha bravo before. The 7 is going to be corresponding to operator 1. And if we scroll back up to the top, and this is going to be corresponding to the truth values of each of the pairs from the first and third displayed symbols. It's always going to be the first and second truth values, as it would be normally, but it's going to be in this case, this is going to be corresponding to the first and third displayed symbols, and this is where the combination of both sets comes into play here. This is where things get a little bit tricky, and we're going to output the color of the middle LED. So there is a little bit of a catch of how we actually need to read this, though. If a CLR indicator is present, which if it is not present, nope, there's only the FRK, it is not true. This is essentially what we have to do for applying each operator to. So operator 3 would be the first truth value, and operator 1 would be the second. However, in this case, we're going to be taking a look at the otherwise rule. So operator 1 is going to be corresponding to the first truth value, and operator 3 is going to be to the second. So let's take a look, and let's actually create our first and third displayed symbols. Let's create that. So we're going to have true from the first one here, and we're going to have true from the third here. So it's going to be a true, true. And then from the second one, we're going to have a false and then a true. So false and then a true. And based off of the information that we just got, we're going to be plugging each of these operators in a specific order. So the first one is going to be applying it to operator 1. So you're going to be going, the true, true is going to be going to operator 1. Whereas the other one is going to be going to operator 3. The false, true. And if there was a CLR indicator, we'd simply just flip this. So now, what exactly do we do? So now there's a second rule that we need to go over because each of these operators could potentially apply to a different position. This, of course, would be different if it was for example, like a false true or a true false. This would be really important. However, in this case, is a false false for the middle LED, so it really doesn't matter all that much. Taking a look, if the bottom LED is lit, which in this case it is, operator 3 outputs to the first truth value and operator 1 outputs to the second. So operator 3 in this case is true, so we're going to be outputting to the first truth value. So you're going to be the first truth value here, and you are essentially going to be the second. That's the way that works. And then otherwise, operator 1 outputs to the first truth value, and operator 3 outputs to the second. That's the way that this works. So now, if everything is true, if everything we've done is correct so far, Foxtrot 7 should work for us. So, if we scroll down to the bottom here, so we need a true true to apply to output 1, which corresponds to the 7. True true corresponds to a not alpha. Not alpha is going to be the true negating to a false. It applies to the second, which in the second position is a false for the middle LED. That's good so far. So now what we need to do is we need to figure out this first one. Now, if we take a look at operator 3, for the first position, is going to be a false true. Now, not imply, if we take a look here, imply 0, 1 does indeed negate to a 1. If we not imply this, this is going to become a false. So this means that we're going to plug this into the first bit, and this means that this does indeed return to a false. And just like that, we have our answer. So now let's plug in Foxtrot 7 to this module, and let's hit it. And just like that is a solved module. So that's pretty much all to this module. It is a logical hellhole, and that's what you're going to be essentially doing. So let's potentially go over one more example. I'm in a mood. I'm in a good mood for one more example, and let's take a look. There are some nasty rules that you can get for the the truth values. In this case, this was actually a really easier one, and I really did not have to go over this operator 3, but of course, for completion's sake, I did. In most cases, you can get the operators 1 and 2 and the 2 and 3 done. You can at least cross off most, if not all, other options that don't work. That's going to be the way that you do things. So let's take a look at a preferably better example. And I'm going to go through this a lot faster because this module does take a while to explain, but hopefully you understand it now at this point. So let us take a look, and hopefully not run into any bugs either. That would be much appreciated. So, on the left side, we have a Bravo, Echo 1, 9, and Delta, Echo 1, 9, Delta. And as I said, there is also the possibility of there being the LEDs in the middle only being unique colors, the LEDs in this case being off on the right side here. But essentially, your key distinction is going to be figuring out from these symbols in the middle here. So on the right side, we have Alpha 3, 8, Juliet and 6, Juliet and 6. Okay, and now let's figure out our truth values for the inputs here. So we have a squeeze. Squeeze is in the first position, and the second position are both here. So next up we have the coffee stain. Coffee stain is going to be the second position, and the truth values are going to be 1 and 3. And the check mark, finally, is going to be position 3, and it's going to be 1 and 2. Okay, this is going to be a little bit interesting. So, taking a look at the squeeze first, the squeeze numerical value is going to be the number of indicators. The number of indicators we have is only 2. That's going to be 2. The next up we have, for the second truth value, is going to be the coffee stain. The coffee stain is the alphabetic position of the first letter in the serial number. Perfect. Nice and easy. That's going to be Juliet, which is a 10. And then finally, the hour of the day plus the month of the year of the time of activation. Oh, good God. Okay, so the hour of the day, I believe this is referring to 24-hour time. It would make sense if that was the case. So in this case, this is currently hour 13 because this is it's 1 o'clock for me right now, 1 p.m., which 12 o'clock is the 12, and so that's going to be a 13 plus the month of activation. This is currently March for me, so that's going to be a plus 3, which is going to be 16. Now, I am going to check the logging for this because I want to make sure that this is correct, and it is on 24-hour time, just for the sake of this. I normally would not do this. In this case, yes, it is 16. That's perfect. That's what we want. So now, let's take a look at our truth values here. Let's figure this out. So for squeeze here, both 1 and 2 occur as digits across the sum of the pairs of values. Occur as digits across the sum of pairs of values. So do we have a potential 1 and 2 occur somewhere across a pair of values? So let's take a look. The sums of the pairs of values. So let's take a look here. Hopefully I'm understanding this correctly because some of these rules are a little bit weird. So both 1 and 2 occur as digits across the sums of pairs of values. So this should be potentially 2 plus 10 is going to be 12. And then 2 plus 16 is going to be 18. And then the 10 plus 16 is going to be 26. Now, I believe what this is referring to is going to be the 12 plus the 18 plus the 26. All of these guys added up together should be 56. And in this case, it looks like it's false. However, I'm going to also check the logging for this one because I'm totally cynical and I really want to get this tutorial done. This should be false. Neither of the truth values are negated. The truth values and negations. Oh, okay, so it is just referring to each of the individual pairs of values. Okay. Both 1 and 2 occur as digits across the sums of the pairs of values. Yeah, so this is referring to the 1 and the 2. So then in this case, we have a 1 and a 2, a 1 and a 2. So this is going to be true. So this is going to be the truth of the first value. I needed to make sure of that, that it wasn't referring to the total sum, which is 56 here, the total sum of the 12 plus the 18 plus the 26. So I had to make sure of that. And then next up, the sum of the three values is prime. 56 is not our total sum. It's simply going to be 2 plus 10 plus 16. And already, immediately right off the bat, actually, you could totally tell that this is not prime because of the fact that all of them are even. And the only even digit, which is actually prime, is a 2. So this is already not going to be prime. So this is going to be a false. So now, taking a look at our next two symbols for the coffee stain moving down here. Exactly one of the values is odd. That is not true because of the fact that we have 2, 10, and 16. That is not true. That's going to be false. And then the digits of the sum of the three values have different parities. Parities is referring to even and odd. So the digits of the sum of the three digits, so let's take a look here. So the sum of the three digits we said was a 28. 28 in this case is both of the digits are even. This is not true at all. So this is going to be a false. And finally, for the check mark, the sum of the three values is one more than a multiple of 4. The sum of the three values is a 28, which actually is divisible by 4. 28 divided by 4. It is not one more than a multiple of 4. If it was 29, however, that would be true. But in this case, that is not true. That's going to be a false. No sum of a pair of values is a multiple of 4. The sum of a pair of values is a multiple of 4. Let's take a look. So we have the 2 plus 10, which is 12. That's already divisible by 4. Easily. Yeah. 4 times 3 is 12. Boom. Done. That's already false. And just like that, we have our truth values for the inputs here. That's perfect. So all we need to do is now take a look at each of the outputs, and then we can start actually plugging away at this thing. So first things first, do we have a TRN indicator? No, we do not. And how many batteries do we have? We only have one battery. Perfect. So let's take a look. So we have green, yellow, aqua, purple. We're going to cycle one space to the right, which is going to put the purple at the front now. And now we have our values here. So we're going to use the outputs. So we have green. Green is going to be the false, false. The aqua is going to be the, no, it's going to be the false, true, excuse me, because it's in the second position. I totally read the table here. The aqua is going to be in the fourth position, which is going to be true, true. And finally, the purple is in the last position, which is going to be our false, false. And these are our outputs that we need to do. So now, let's do what we did from beforehand. So let's try and figure out and see if we can eliminate any options from each of these operators here. So operators 1 and 2. So 1 and 2 are going to be used of the left set. So from the left set, we're going to be using these operators here. So here. So let's highlight everything. So Bravo is going to be here and here. Echo right here and right here. 1, 9, and Delta. I did not mean to do that. Next up, so operators 1 and 2 have the left set, which we just did. Apply respectively to the first and second truth values of each pair. So this is going to be us setting it up right here. So the first pair of values is going to be the true and the false from the first positions of each of these guys here. And then we have the false, false from the second position of each of these pairs here. Perfect. So now what we're going to be outputting is going to be outputting to the left LED. So we're trying to get to there. Okay, so let's try and get a false true, and this will be interesting. Now, immediately right off the bat, XOR specifically wants us to have exactly one true to be true. True false gives us a true in this case, so that's going to be a false because of the fact that we need to have this to be a either a true true or a false false for this to actually be false. So in this case, 1 is not going to apply here, because of the fact that this does return true, and in the first position we need it to be false. We do not want this to happen, so goodbye. Next up, not imply by. If we do not imply by for true false is going to be a 1 0, which is going to return as a 1. However, if we negate this is going to return as a false. So this is actually true so far. However, for operator 2, let's see what happens. For a false false on an implication, a false false returns as a 1. This actually is indeed true, because we need to have a false true from this, which 9 is a possibility of returning as true. So this is going to be possible to use in the later on series. Let's see if we can get rid of anything else. So taking a look at not B, of B, for example, operator 1 is an and in this case corresponds to both of them need to be true, else it will return false. In this case, that will return false because of the fact that there's at least one false present. So this is going to be false, okay? And not alpha for this one here is simply going to be negating the A position in this position. So that's going to be negating this false to a true, which also does return to a false true. So Bravo is also a possibility here. So this is exactly what I mean by there is a possibility of there being multiple characters which can be used in each of the left sets, in which case that third step is going to have to apply. So we don't know exactly which one we're looking at quite yet. Next up, let's try and see if we can get rid of Echo and Delta, because I believe that we're going to be able to in some way, shape, or form. Unfortunately, X nor wants us to have both the characters be exactly the same, and in this case, both the characters are not exactly the same for this first set, in this case being true, false. So this is actually going to return to a false for X nor. Good. Okay. NAND, however, if we take a look here, NAND is going to be if at least one of the indicators is false, it will return true, which in this case is also true. So delta is also another possibility of which we can consider here. So this is actually another nasty example. This is a nasty example where you can have three different possibilities. And for echo, finally, a true false on an implication. A true false on an implication is a 1 0, and that's going to return to a false, which we do want. And alpha is going to return as a false for the second position. So this actually does get rid of the echo. But we do have three different symbols of which we're going to be comparing for the left set on the third step. This is where things can get a little bit tricky to do, essentially, and that's kind of where things can get a little bit annoying. But at least we figured out that we have three different possibilities of which can work on the left side, but only one of them will work, which we will figure out later on. So now let's take a look at our second step. Let's try and see if we can get rid of potentially all like 4 different values here and see what we can do here. So now we're going to be using operators 2 and 3 on the right set, for example. So let's space these guys out. And we're going to be taking a look at the second and third displayed values. So it's going to be the false, false, and the false, false here. And what we're going to do is we're going to output the truth values of the right LED. So we need to do a false, false, and a false, false to give us a false, false, which is not as simple as it looks. So we have alpha, and this is going to be operators 2 and 3 that we're going to be using here. So alpha, 2 and 3, 3 and 8, 3, 8, and 6, and a Juliet. Okay, this will be interesting. So we have false, false for our first one here. We have a false, false, and a false, false. Let's try and figure this out because this is the first bit right here, false and false, and the second bit, false and false. So let's take a look. 3 we can already get rid of because they both are the exact same bit. We want those both to return false. However, false, false will return as a true. We do not want that. So 3 is going to be saying goodbye. Goodbye. Okay. Next up, for 6, 6 we have the X or and nor. However, nor immediately, if we both have a false, false here, so that means we can get rid of the 6 because of the fact that the false, false for nor returns as a true. As you can see here, 0, 0 returns to a 1. This is exactly what we don't want, so we don't want the 6. Goodbye, 6. X nor, same case as we had from beforehand, from the 3, returns false, false will return true. We don't want the 8. Goodbye, 8. Perfect. Next up, alpha. Alpha actually looks pretty promising. X or we need to have we need to have exactly one of them being true, which we don't have it for the first set. We have the false, false here. So that's going to return to a false, which is what we want. And we need to have both of them being exactly true, which actually does return as a false, which is exactly what we need. So that's going to be false, false. That's good. That's a possibility. And finally, taking a look at Juliet, operator 3 sticks out like a sore thumb for operator 3, not and. If we happen to have at least one false, that will return as a true, and in which case we have both false, false for the second operator, the second set right here, operator 3. This is actually going to return false, and alpha is going to be guaranteed to be used on the right, excuse me. Now, we're going to have to use the third step because of the fact that we have 3 different possibilities which can be used in the left set. That's what we're going to be using here. And this is where it all comes down to this. So let's take a look. So first off, do we have a CLR indicator? We do not. And the bottom LED is not lit. So we're going to be taking a look at both the otherwise rules here. So we're going to be using the left set for operator 3. Operator 3 is going to be our left set. And we're going to be using the operator 1 of the right set. So we're going to be using guaranteed operator operator 1 of the right set, right here, and we're going to be using operator 3 of the left set here. So we're going to be using Bravo, 9, and Delta. Okay, and our goal here is to figure out exactly what we need to do. So we're going to be using the middle LED as our truth value. So we're trying to get to a true true. And we're going to be using the first and third displayed symbols, but we need to figure out our ordering here. So first things first, let's actually get the first and third display symbols here. So we have a true false for the first positions here, true false, and then a false false for the second positions of each of them. So now, in this case, we're going to be taking a look at the otherwise rule because we do not have a CLR lit indicator. So we're going to be applying operator 1 to the first true values and operator 3 to the second. So we're going to be doing operator 1 for true false, op 1, and then operator 3 for the second. And now, since the bottom LED is not lit, we're going to be applying operator 1 goes to the first true values. So they're going to be the first true values right here. And operator 3 is going to be going to the second. This is what we're looking at here. So now, operator 1 is our alpha. Alpha is going to be simply taking a look at this guy right here. It does give us a true, which is exactly what we need for the first position. That is perfect. That does confirm alpha is indeed our answer for the right side. However, for operator 3, let's take a look at our second bit. We need to return true for this position here. And we can already rule out 9 because 9 wants us to take a look at Bravo. Bravo will return as a false in this case. So we're going to simply get rid of 9 here, just like that. Next up, implied by or not implied. Now, we can take a look at alphabets here. Not implied by, in this case implied by, is going to be a false, which returns to a true, which means that if this was done correctly, we should be able to have the other character, the not implication, the false, which does return to a true not being negated is going to return to a false. So this means that the implication by is our answer. So we're going to get rid of delta, and we're going to submit into the module B and A. So now let's set that up. It's already set up. We hit submit, and just like that is a solved module. As always, thank you guys for watching. Stay crazy, stay cool, and I will see you guys in the next one. Bye-bye.